Well, first of all, thanks for that quick introduction, and I want to give a big thank you to Fabian and the organizing committee for putting on this conference, and grateful to see all of the faces in the room and all the folks that are participating online. So Fabian asked me to talk about cropping system diversity and nitrogen. It's something that we've been starting to do a bit of work on with a couple of projects recently at the experiment station down in Lamberton. And so when I really wanted to focus in on some of the nitrogen aspects, a lot of the work that we've done historically, going back almost 20 years, relates back to, very specifically back to nitrogen management through tile drains, drainage, and that kind of thing, which is a lot of the work that I personally do. Some of the more recent work we've been working with in terms of cropping systems really relates more back to carbon and nitrogen and water and the combination of those things within the cropping system. So in my talk today, I'm gonna start out with some of the more historical work that we've done and share just a few results from those things. Some of it has not changed in terms of results, as you'll see. And then I'll end with some of the newer stuff that we're starting to embark on. So I just want to acknowledge Dr. Axel Garcia and Greg Johnson, who are a couple of collaborators with me on some of the newer work that we're doing. So the first thing I want to do is define what I want to have as you guys thinking about what cropping system diversity is. There are lots of thoughts out there, just like people thinking about the term soil health and soil quality and what does that mean. So I wanted to kind of lay this out right at the beginning. So you see that there are really kind of four things that I'm kind of designating as could be part of the definition of cropping system diversity. One is the obvious, the number of crops in the rotation. So most people in southern Minnesota are growing two, corn and soybeans. But as you start to add things like wheat and alfalfa, you diversify that crop rotation. As John was just talking about, and others have talked about, when we start adding cover crops to the cropping systems, that's another way to think about cropping system diversification. Integrating livestock into those systems as kind of was one of the questions, John, about maybe using that as a grazing tool for the Cura clover. Also thinking about grasses and legumes that are perennials out there, again, alfalfa, but also some of the biomass crops that are out there, thinking about some of those newer things like kernza that are coming along. And then thinking about the length of time between soil disturbances. And what I mean by that is that I remember back many years ago when I first started with the U, visiting with George Ream, and George is kind of a legend at the U of M with fertility. And George talked about rotational tillage and said, maybe we ought to think about at some point in time, thinking about rotational tillage, that we have no-till for a while, but then maybe it might be advantageous as we get maybe stratification of nutrients to go in and every so often till that. So those are some things that I want you to kind of keep in mind in terms of thinking about a broad definition of cropping system diversification. So I'm going to talk about four specific studies that we've done over time. The first one is a cover cropping trial that we did with rye and a corn soybean rotation. Another one is a cover cropping trial, which was with multiple species in a corn soybean rotation. The third one is a drainage study that a grad student of mine did back in the early 2000s, where we were comparing two really large pieces of land and looking at the cropping system diversity that existed between those two pieces of land as part of the results of what we saw coming out in terms of water quality in that particular story. And then the last one is going to be some more up-to-date data that we're really just starting to really embark on in our long-term ag research network nodes across the state. And I'll talk about that one again last. So this first one, and as I set each one of these four up, I'm going to talk initially with a slide to give you a little bit of backstory. And then I'll go through some of the data that we had collected over time. And then I'll kind of come up with a summary slide. So you'll see this repeating pattern. So this project was between 1999 and 2001. This was a rye cover crop study on our drainage plots at Lamberton. We drilled the cereal rye into the corn and the soybeans. We had both crops present every year, and we had cover crops drilled into each one of those systems. We measured grain yield, we measured cover crop biomass, residual soil nitrates down to 4 feet. We also looked at drain flow from our drainage plots and flow weighted mean nitrate concentrations and nitrogen loads from those systems. What was really, really cool about this particular period of time when we were doing this research, as you see up on the screen right now, is thinking about the precipitation. So over those 3 years, we actually had a wet year, a dry year, and a much more average year. And so we basically had the 3 extremes that we might expect to see when farmers are out there cropping, and they actually happen for us in a 3-year period. And I might point out, as I'll get toward the end of the talk, that these cycles, fortunately for us researchers, sometimes repeat themselves and make our lives a little bit easier to be able to show some of our data. So the next couple of slides are going to be just sort of the summary slides of what we found from that particular trial. So this is looking at the actual subsurface drainage from the plots that actually had soybean, corn, or corn and rye, and corn and soybean. And what you see there is that the 2 sets of treatments that actually had the corn, rye, soybean, rye rotations actually had statistically significantly lower drainage outflow from them. So as John sort of alluded to in talking about the Curie clover, that those cover crops can utilize some of the moisture that's there and then actually helped us reduce our drainage outflow in a significant way over that 3-year period. What was more interesting was looking at the nitrate loss. So when you look at this data, the corn, soybean, rye, and the soybean rye, the corn rye were statistically significantly lower than what we had seen coming out of the soybean crop. Now you might scratch your head and say, well, why was the nitrate coming out of the soybean phase of the rotation higher than what came out of the corn rotation? So this is what we saw in terms of what the carryover nitrogen would have been. So the corn that you see there had been soybeans the previous year. A lot of that soybean nitrate had been scavenged by the crop. So the corn was really using the nitrogen that was applied, and it wasn't leaking out of the system. Whereas the soybean, there was some residual N. That N was able to move through the profile and then out the tile. So the corn was no different really than the corn and the rye, and the soybean than the rye. Now, when we started looking at some of this, and I apologize for these metric units, this is going back quite a few years to tables and figures that were just going to be too much of a hassle to really kind of change for me. But when we start looking at the yields up on that the upper left figure there, basically what we're seeing is that there were no differences in corn and soybean yields, whether we had a rye cover crop planted in there or not. When you look at that lower right table, table number 3, that basically is showing that if you look at it, the dry mass in megagrams per hectare, essentially what you really want to get a grasp of here is not necessarily what those numbers are, but the magnitudes of the sizes of those numbers when you look at it from year to year to year. And so when you look at that 1998 to 1999, that was our closest to average year. And we had really, really outstanding biomass production in that particular year. When you look at the 1999 and 2000 growing seasons, it was less than half of what we had seen the previous year. And that actually happened to be our wetter year. So the wetter year was a little bit more challenging for that rye to be growing and be established. And then, of course, 2000, 2001 tended to be our dry year. And we had essentially kind of a negative impact of that dry weather on the biomass from the rye. And if you also look back up in table 2 in 2001, those were the lowest yields that we ended up having, in particular for the corn, just because of that dry season that year. So one of the things that I don't have listed in this summary, which has been repeated over and over and over through the years after we published this work, was one of the things that we kind of determined from our earlier work in that early 2000s was that at least here in Minnesota, under our cool conditions, we can establish successfully a rye cover crop 1 in 4 years. We've got really great conditions where we can do that, and that really kind of still stands today. So that first sort of paragraph, which is far too long, basically is saying that precipitation and temperature are the controlling factors in getting that cover crop established, and then it being successful in either growing or being able to reduce the nutrient losses from those systems. And in that particular set of years, as I said, we didn't see any negative yield impacts from the rye that was grown in those systems. In the multiple cover crop study, this is one that my colleague Axel worked on in some of our plots. This was 2016 to 2018, obviously much more recent. This was actually published in a master's thesis by Hannah Rush that you see there. I've put the title up there just in case, as this is made accessible forever on the internet, that you want to look that up, you'll be able to find it. But these cover crops were seeded into corn while the corn and the soybeans were standing during the early V4 and V6 time. And there were a number of different cover crops that were planted. So there were monocultures of annual rye and cereal rye planted, plus those same two cover crops along with mixes of crimson clover and forage radish, as well as a no cover crop treatment. So I put the site characteristics up here because this is kind of a sort of a first introduction into some of the long-term ag research nodes that I'm going to talk about in our last study. So we actually have these at 3 different locations in the state of Minnesota, up in Grand Rapids, at Lamberton, and at Waseca. We have some clay loam and loam soils. You see that there's quite a range in the percent organic matters, certainly low up in the Grand Rapids area and considerably higher at the Waseca and the Lamberton site. So these are alpha sols that actually developed up in the Grand Rapids area, and the mala sols down here in the southern part of the state. There's a range of drainage classes. These are the natural drainage classes. Of course, at Lamberton and Waseca, those are artificially drained soils. We've got tile underneath them, whereas up in Grand Rapids, we do not. You'll notice there that the annual precip at Grand Rapids and Lamberton are quite similar. Couple hundred more millimeters over at Waseca, and you can obviously see that from a temperature gradient, we've got warmer conditions down in the southern part of the state compared to the northern part of the state. So when you start looking at some of this data, what's really interesting here, this is grain yield for corn at that site across all of those early seeded cover crop plantings. And those letters A that are in every one of those bars tells you that there's no statistically significant difference among all of the yields, which matches not unlike what we saw and showed from the early 2000s data, that we really don't see a whole lot of negative impacts on the yields of corn and soybeans, in this case corn, when we're growing some of these cover crops. What is kind of interesting, again, in the short 2 years that they did this project, is related to the cover crop biomass. There's drastic differences between 2017 and 2018, and there's differences between the 2 different types of cover crops groupings that were grown. So the annual rye, the AR groups versus the cereal rye groups. In particular, when you look at the top row, that's all up in Grand Rapids. The annual rye and annual rye groups tended to perform better than the cereal rye groups. At Lamberton, they performed equally well in 2017, and in Waseca, and actually in both years, they performed somewhat more poorly. Now, when you look at 2018 for Grand Rapids, for Lamberton and Waseca, there was fairly poor performance in all 3 sites. A lot of that can be attributed to the wet conditions that we had in terms of late springs and getting these things established at V4, V6. You know, when you start thinking about 2016, 17, 18, and 19, we really had 4 years of wet conditions, and they progressively got wetter as we got into 2018 and 2019, and that certainly had a negative impact at all three sites in 2018, which was generally overall wetter than in 2017. So here's where the results become a little bit more interesting in terms of looking at what some of the results are. So the blue bars represent the monthly precipitation. The colored bars there represent the cereal rye, the cereal rye with crimson clover, the cereal rye, crimson clover forage radish, and the no cover. And so what you see is that in particular in 2017 at the Grand Rapids location, 2017 at Lamberton, and 2017 at Waseca, that no cover yellow bar indicates that there's a lot higher nitrate concentrations. And so the part of the goal for this work was to look and see, was there some sort of reductions among the mixes of cover crops for reducing nitrate in these happen to be actually suction cup lysimeters. It wasn't a tile system. And there were some really nice declines in using those cover crops. In 2018, you see it's kind of a mixed bag at all three of the locations, considerably wetter, particularly at Lamberton and Waseca, and there was no separation in terms of nitrate losses there. They were all about the same. Poor stand establishment really because for the cover crops really did not actually help in taking up any of that residual nitrogen that was there due to those wet conditions. So the things that I kind of gleaned from looking at the study and talking with Axel is that one thing was pretty nice in terms of the establishment of the rye and those mixes was that being able to do it in the early stands rather than trying to drill it after season like we had done in the early 2000s was pretty successful. And it also helped looking at reducing nitrate in the soil solution at all three studies. At least it was good in 2017. We did see some differences in the concentrations, and of course, coarse soils up at Grand Rapids created a bit of a challenge because water tends to move through those a lot quicker than they did in the soils at the southern part of the range there. And then, although they didn't identify what the thresholds were, there was some sort of an idea that there was a threshold for cover crop growth that particularly was not achieved in 2018 because of those wet conditions, which really kind of disallowed reducing the nitrate concentrations in solution. So when it comes back to the point that I made about that first study that we did back in the early 2000s, it was all really about precipitation and temperature, of getting these things established and getting them established well so that they'll actually work, at least from an environmental benefit, which was the focus of these two particular projects. This next one was one that we did sort of almost in sort of the mid-2000s, 2002 to 2004. In this particular study, this was a much larger scale. So all these others were essentially small plot work. This was at essentially 160 acre field size plots, if you will. We had a conventional system, which was a corn, soybean rotation, generally speaking, with inorganic fertilizers. And then we had an alternative one, and basically that was about the same area, 160 acres of organic production, which had a lot more cropping system diversity, of course, dominated by corn, soybeans, small grains, but there was also alfalfa and a number of other crops that I'll show here in a minute. Again, this was one of those really nice kind of a studies. 2002 was relatively dry. It was just a little bit under average. 2003 was considerably drier, and then 2004 was a pretty wet year. So we had a diversity of weather patterns in that same period of time. So generally speaking, like I said, the conventional was dominated by corn and soybeans, and some of those the other crops that I mentioned in the alternative one were buckwheat, flax, and clover, hairy vetch, and some rye that was grown to seed out there as well. So in this particular case, this is just looking at the cropping practices, looking at the crops on that left side axis, the years. The AL means alternative, the CN means the conventional. And even though these are in units of hectares, the idea is that you can actually take a look and get a pretty decent idea of where the dominant crops were. So of course, in the corn soybean rotation, in essentially all of those years, corn was the dominant, soybeans was the second most dominant, and in the conventionals, there were very few small grains, very little alfalfa, and no native grasses. Whereas in the alternative one, it was much more of a bit of an even split, really between corn, soybeans, and then or corn and small grains, and then soybeans and alfalfa and the native grasses. So there was a lot more diversity, even though it was somewhat smaller on that organic site. The nitrogen applications, of course, being organic, we ended up using alternative sources there. So there was no commercial fertilizers. It was all hog manure, beef manure, compost, legume plow downs from the alfalfa. And then we used anhydrous ammonia on the conventional side. So when you start adding all of the nitrogen rates up, even though they varied a little bit from year to year, they're actually really quite close when you look at the total amount of N that was applied between both of the sites over that 3-year period. So this is actually what the sites look like at the research center. The yellow lines on there represent the subsurface drainage lines that we have there at the research station in Lamberton. And the red points articulate the dots where we were actually monitoring the subsurface drainage from the site. Here's some of that precipitation data that I had mentioned a little earlier about the dry, drier, and wet years that we had over those 3 years. So when we start looking at drainage, 2004, as I mentioned, was a pretty darn wet year. So we lost a lot of water, in particular out of the conventional system, actually more than twice as much out of the conventional system than we did out of the alternative system. In the dry year, there was really no water there. There was no driving force to push water into the tile, so they were about the same. And we saw slightly more coming from the conventional. So the big difference, especially that was really articulated in 2004, was really for us thinking about the diversity of the cropping system, where we showed that we had a lot more small grains and alternative crops growing out in that organic system, the alternative system, as we called it, was really useful in terms of early season uptake of water and nutrients, as you'll see in a second here, in terms of reducing the outflow of drainage from those systems. And when we look at the nitrate leaching that we saw in terms of at least concentrations from the systems, we see that generally speaking, they're less than half from that alternative system compared to the conventional system out there. Again, not because of the necessity that there was less nutrient put on each one of them. As I pointed out, it was about the same. But when you start looking at the synchronicity of when the crops were out there growing and when they were using it, it did make a bit of a difference. At the end of the day, we were looking at the actual nitrate loads. And over all of the 3 years that we looked at this, that alternative site with the higher diversity of the cropping systems was considerably lower and significantly lower in 2002 and 2004 compared to 2003. So, you know, this is a story that keeps repeating itself in these first 3 studies. That precipitation obviously is a really key factor, in particular when we start thinking about the water quality aspects of nitrogen and nitrogen loss. And that as we get more cropping system diversity out there, whether it's through those cover crops, as I showed in the first 2 studies, or in this particular one, that we can see some relatively nice reductions in nitrogen loss from implementing more diversified systems out on the landscape. This last one, I'm going to show a little bit of water, and it's going to be there's going to be a lot more inference in this particular little section of the talk, just because a lot of this data is really kind of hot off the press and much more recent. We just don't have quite as many years of data to really take a look at this point with the water respect. So as I mentioned, these are Grand Rapids, Lamberton, and Waseca nodes of our long-term. All right. Having trouble with the earpiece here. So this project has been going on since 2014. I'm only going to focus on data from the Lamberton site, and maybe I'll just hold this because it's. Oh, okay. I've never been told I've had a quiet voice.
Quiet down.
Yeah. So the other piece of this is that this particular project has 7 different cropping systems, or 6 actually, if you're up in Grand Rapids. You see them all listed there. The corn alfalfa cubed just indicates that we've got alfalfa 3 times, or for 3 years after that. And we've got a corn rye, soybean rye rotation, as well as a polyculture. And then the pasture hay mixture is what's up in the Grand Rapids site. So this is a kind of a busy slide, and you're not going to be able to see all of the details obviously on it. But what you're basically looking at the top is 3 rotations. The 2 on the left-hand side are from a corn crop. These are bi-weekly soil moisture measurements down to 40 inches. All right. So what you've got is you've got 4 different colors there, 5 different colors that represent the different depths of the soil profile, right? And the thing that you're looking at here is on the left is the corn and a corn soybean rotation, and then the middle one is corn soybean wheat, so that's corn and a corn soybean wheat rotation, and then the last one is the polyculture. So we're not going to dive deep into details on these, but what's pretty interesting to look at is if you look at the slide, you'll see that the corn and the corn soybean rotation had a lot less soil moisture throughout the growing season compared to the corn soybean wheat, keeping in mind that the wheat from the previous year was harvested in late July, early August, and had been fallowed for the rest of the year. So there was no evaporation, there was no transpiration, which is transpiration's the big water usage there. So we were able to actually build more moisture into that cropping system, which in a drought year of 2021 is pretty amazing to see the amount of moisture that was in that cropping system during the whole entirety of that growing season compared to the one that was right next to it that had been in soybean the previous year, right? So the water use was quite a bit different. And the polyculture out there is kind of our baseline. And that was somewhere intermediate between the water use that we had from the corn soybean and the corn in the corn soybean wheat rotation. Now, what you're seeing at the bottom is the same data, all right? But the slide at the bottom is actually taking the 2 deepest depths out, right? So now you're looking at a lot more of what the activity was within the other 2 systems, or within all 3 of these systems. And especially what you'll notice is if you look at the corn, soybean, wheat image right there in the middle, there's a lot more blue, which represents the top 4 inches of the soil profile. It's much wetter for the corn and the corn, soybean, wheat rotation than it is in the corn for the corn, soybean rotation, which is the one on the left, right? You can see that there's a lot more water distributed throughout that entire profile from the corn, soybean, wheat. As I said, a lot of that is recharged probably from the fallow period the year before. And when you start looking at that polyculture, it's a lot more stable, right? So that's just that 1 year's worth of data for that. These will be a lot easier to see. It'll probably be really difficult to read the numbers, but again, what I want you to be able to do is to see basically the trends. So this is brand new data. I have not run any statistics on any of this yet. So these are basically just the raw data that we've got coming out. So the top is the mass of carbon in the soil profile from time 0, which was when we started this project back in 2014, and time 1, which we're marking as of 2020. So it had been about 6 years. And so we were trying to look and see, did we see any gains or increases in carbon stock in those soil profiles after we had changed the cropping systems from just a normal corn soybean, which all these fields had been in for 50 years. So the corn soybean on the left, really, there's not a lot of change there in terms of the overall total in the profile. The corn soybean CC, that's the corn soybean with a cereal rye cover crop. You can see that there's a bit of a decline of carbon in the deepest depth there, but it's a little bit more accumulation of carbon in the other 3 depths above that after 6 years. The corn soybean wheat is somewhat similar. We see a slight increase in carbon in that profile, and it occurs apparently at every one of the depths that we're seeing some incremental increases in carbon. Carbon equates to being able to look at better infiltration. Better carbon to nitrogen ratios can help release and mineralize nutrients out of the system, provide better stable aggregates and things of that nature. The polyculture, you see the biggest change, really certainly related to the continuous cover that's out there in the rooting systems. The panel below on the bottom there represents the nitrogen. The nitrogen in these things is at a much lower concentration or a much lower mass than we see the carbon when you start looking at the scale on the left-hand axis. But what's pretty amazing is that, again, I don't know if these are statistical or not yet, but we start seeing some fairly dramatic increases in nitrogen in the profile. When I first looked at this data the other day, it puzzles me a little bit because we have not increased nitrogen rates on these trials. It's similar to what it has been for all these years. There may have been a slight decrease of nitrogen applied to the corn, soybean, wheat, just because the wheat requires less than the corn, but we actually see an increase in the soil nitrogen. And what I'm showing you is the total nitrogen. We haven't partitioned this into inorganic nitrogen, which mainly would be nitrate or ammonium, and then the organic nitrate or nitrogen at this point. So what the gain is in nitrogen in these profiles over that 6 years, I'm not sure yet, but I think it's pretty fascinating data nonetheless. This last 2 slides I'm going to show real quickly. This is just kind of a slide to make you think a little bit about the carbon to nitrogen ratio, because that's going to be the last data slide that I'll show. So if you look at the bottom of this slide, this is Save Our Soils. It's just it's a publication that I found that had a really nice sort of visualization of thinking about carbon to nitrogen ratios and the idea of mineralization and immobilization in terms of rate. So if you look at the bottom of that blue or pink column there, it says slower and faster, okay? So as you change your C to N ratio and you start looking at the little stars that go across, you get to this equilibrium level between, say, 20 and 30 in terms of the C to N ratio right in the middle of that graph. As you get down to lower than 20, or you get into that mineralization, and it becomes faster the lower the C to N ratio is. So if you get a C to N ratio of 5, it means that your mineralization is happening really, really quickly. So there's a lot of turnover of that carbon that's there quickly. If you get a C to N ratio of greater than 50, you push over to the other side where you have immobilization. So basically you're immobilizing nitrogen in that profile into the little bodies of the little microorganisms that are out there, and it's not available to be able to be utilized by the plant. And it's important to kind of get some of these numbers, at least to think about faster, slower, and what those numbers are when we start looking at our calculations for carbon to nitrogen ratio. Again, it's kind of like when I was listening to John, I don't have all the answers as to why these things are happening, just because it's new data and I haven't had enough time to really think about it in a deep way. But one of the first things that you see with all 3 of the crop rotations, the corn, soybean with the cover crop, and the corn, soybean, wheat, is the carbon to nitrogen ratio changed over 6 years. Or at least if it's not statistical, it numerically declined, right? And when you start looking at some of the numbers, for example, if you look at the corn, soybean, wheat, in that bottom depth, the original carbon to nitrogen ratio was around 32. Now it's around 22, right? It means that it went more toward a mineralization side of things and that it's getting faster, right? Why that's happening at this point, I don't know. I can't explain right at this moment. But what was also kind of interesting is the stability of the polyculture one from when we established it to where it is now. It's pretty stable. It's hardly changed at all. Usually, I think, as most of us researchers would say, we start a project looking for answers, and sometimes we come up with more questions at the end than we had answers to begin with. But I would argue that, or at least say at this point, this is the beginning of some what I hope will be some rather interesting and useful information to share with you guys in the future. So anyway, just a quick summary. Soil water content was highly variable among those cropping systems, and that was in a drought year. We saw the most dramatic differences in water content were near the surface. That was that bottom panel that I showed. And the questions that I raise about that is it related to the carbon and infiltration in some of those systems where we've got cover crops or more diverse systems where we've got corn, soybean, and wheat compared to just a corn, soybean rotation? We haven't gone out and measured the infiltration, but obviously we did measure carbon. The mass of carbon and the mass of nitrogen varied quite a bit by the cropping systems. The carbon increased for most of the cropping systems. The nitrogen increased for all of the cropping systems. Again, what the speciation is, I don't know yet. And that carbon to nitrogen ratio decreased from time 0 to time 1 in all but the polyculture, which was a stable system, at least at this first 6 years. So final thoughts when I think about this, and I'm going to kind of nail this from the standpoint of thinking of initially about cover crops from that first study. They have been shown and talked about to be difficult to establish, and they still are, but they can have some positive benefits, particularly for water quality and soil carbon, as we've seen in some of the last data I showed. The multi-species cover cropping systems has a positive impact on the water quality, at least according to those suction cup lysimeter leaching data that Axel shared with me. The more diverse cropping systems compared to corn and soybeans in that last study showed a greater carbon and nitrogen stocks, and that C/N ratio was pretty stable. So I think as we think about diversification of cropping systems, I think there's a lot of different places that we could be thinking about related to water quality, carbon, soil health, that have some potential pretty positive aspects to them. And that's all I got. Oh, all right. Well, yep, I see them up there right away. So the question, when were the cover crops terminated in the spring? That's a great question. All of the cover crops were terminated if they were not winter killed. So the annual rye cover crops, the clovers would have winter killed in those studies. The cereal rye cover crops would have been about 2 weeks before corn and soybean planting. And those were always done with glyphosate. So we sprayed Roundup on them. So let's see, because of C/N ratio is, it seems to me that N management should be included as a soil health practice. Thoughts? You know, I think there's a good argument for that in terms of, you know, when you think about soil health and you think about soil health metrics that are out there, and I'm not necessarily a soil health or a soil health metric person, but what I will say is that these are really complex systems that we're studying, and you farmers that are either in the audience in the room or online listening to us talk are really inherently complex. And you know, we don't understand them as much as we think we understand them. We try to do our best. And certainly thinking about nitrogen management, the N that's there and how it's interacting with carbon and nitrogen, especially with the C/N ratio, seems like it would be a really good piece to include in there in terms of soil health practices. Oh, okay, I missed whatever that. Oh, there, it's back. What tillage was used in the last experiment described relates to residue breakdown. Okay, so in the L-Tarn sites, the tillage varies at all of the different sites. Where we have cover crops, we do strip till. In some of the other crops, we do essentially a deep ripping with or a disc ripper as a normal farmer would do in some of the general cropping systems that we have out there. So it's a variety of things just depending on what the cropping system was. So. Okay. Yeah, Mark.
With the cover crop and silviculture, complexity of establishing cover crop may have some acceptance. The use of wheat in the rotation that kind of got better.
Yep, it did.
Would you attribute that, or is there something else you attribute to through wheat in the rotation?
Yeah. So again, it's really complex, Mark. The question was, thank you. So the question was in thinking about the trickiness of establishing cover crops and then having the diversification of having wheat in a rotation, maybe rather than a cover crop, seems to change and improve the carbon to nitrogen ratio and the carbon in that rotation. The point would be is that when we look at that, what sort of the question mark you had is really kind of, I guess my interpretation of the question was, so why is that happening and what's the cause of that, if you will, in some of those improvements? And I would say that by and large, a lot of it has to do with the rooting systems and the differences in the rooting systems that we have between the corn and the soybeans versus a wheat crop, which has a much more fibrous root system, explores, a lot more soil than say the corn and the soybean, especially the soybean with a little tap root on it. So, I think a lot of what we're seeing in that long-term study is really below ground, what we don't see related to roots. Is where I think all the action's happening. We've done some root measurements. We've published some stuff on roots, but we really haven't gotten, and that was related to water. We really haven't gotten into asking the questions about roots and the carbon, the nitrogen, and the water sort of interacting with each other. And that's kind of where we're trying to go now, actually, is to be able to think about those questions like you asked. I don't have a great answer for you, but I think it has to do with roots. So.